Every rotating machine has a rotor, right? And every rotor in the real world is never perfectly balanced. There can be multiple reasons for that. So what can be the multiple reasons? The multiple reasons can be the material is, isn't perfectly uniform. It can be, uneven welding. It can be, blade has been eroded, or maybe the reason is uneven deposition of the dust, so whatever the cause, the result is same. So okay, so what is the result? That the center of mass is not sitting on the center of rotation. So what will happen in this case? The machine will start to vibrate. So we are covering balancing across two videos. So this video is the concept, or you can say the theory, and we are going to understand exactly what unbalance is and its types, and also we are also going to see some data, that how it looks like in the data. And the next video, it will be a fully practical, and there you will be seeing that how actually to perform the balancing in the field step by step by using the vibration analyzer. So I want to make you a promise right now to all of you that once you go through with these two videos properly, you will never ever struggle with the balancing again. Not the theory, not the field work, you will have all the full picture. Okay, so let's start from the beginning. Let's first discuss that what is rotor unbalance. So a perfectly balanced rotor that has its center of mass exactly sitting on the axis of rotation. Okay, so what it means, that when it spins, every part of it at a constant distance from the rotor. That means it's perfectly designed. So, and there is a no centrifugal force is generated. So in that case, what will happen, that the bearing will carry only the weight of the rotor. It's known as that machine is very smooth, or you can say machine will run very smooth without any centrifugal force. Okay, practically this is, you will not find this thing in the field, but just to explain. Okay, so now let's do one thing. Now move that center of mass just slightly off the rotation axis, even let's say by a fraction of a millimeter or a few microns. So now what will happen? Now when the rotor will spin, the heavy spot generates a centrifugal force, of course, right? That rotates with it when pulling towards the once per revolution, or you can say the each revolution, right? So that rotating force is transmitted through the shaft into the bearings, of course, right? Then into the machine structure, and after that what will happen? We'll be feeling it as a vibration. Okay, so here the key thing to understand is this, that the force is rotating. Okay, so it isn't pointing in the one direction, it sweeps around in a circle once per revolution. So that rotating once per revolution forcing function is the signature of what? Unbalance. Okay, and the heavier the unbalance, the faster the machine is spin, the larger that force will become. Okay, so unbalanced force grows with the square of speed, or you can say that double the speed, the force will become 4 times. Okay, that's the reason that why high speed machines are so sensitive to even a tiny amount of unbalance. That's why it's very very important to deal in a very professional way, because it's by mistake if we have put on the weight while doing the balancing procedure in a wrong in a heavy spot area, so the vibration will be shooting up very high, and it may turn into disaster, right? So this is unbalance. Okay, now we'll be discussing the types of unbalance. So normally there are three types of unbalance. Here we are going to discuss the fourth one also. I will just giving you the name of the fourth one also. So first one is the normal, that is the static. Okay, the static unbalance. So what is the static unbalance? Is the simplest type, you can say. The heavy spot is at one angular position only, and it exists in a single plane across the full width of the rotor. Okay, so if you place the rotor on the frictionless support and let it come to the rest, it will always rotate. So the heavy spot always sit at the bottom. Okay, that's why it's called the static. So you can detect it even without spinning the rotor. So that's why normally you have seen in the field that even with the light or the rotors which you can easily rotate, you can see that the technician or the engineer will be trying to rotate the rotor again and again one, and it try to find out the heavy spot. Okay, and based on that he is going to decide at which angle or which location he have to put the correction weight. Okay, so this is known as the static unbalance. So in the vibration, what you will see here, you will be seeing a dominant 1x in both radial directions. Okay, what are the radial direction? Horizontal and vertical directions are known as the radial directions. Okay, so the phase readings at each bearing are in phase. That means once you will be or you can say that if I will put the sensor one sensor in the horizontal side of the driven side and another sensor in the non-driven side in the horizontal side, so I will be seeing that the both the readings are in phase. So you can consider a little little bit 20 degree 30 degree up and down. Okay, so let's say that one side the phase is 0 degree, maybe another side you will be seeing maybe 20 degree. Okay, so if you carry out the difference is 20 degree, so that means it's okay, plus minus 20 degree, 30 degrees will be considered as a in phase. Okay, but if you same thing do with the single bearing, let's say that you will putting the sensor in the one sensor in the horizontal side of drive end side and another sensor in the vertical side of the same bearing drive end side, so you will be getting 90 degree phase shift. Okay, or you can adjust plus minus 30, because it's not always exactly 90 degree, there will be some variation. Okay, so the same thing, if you just pull on this same setup to the ND side, there also you will be getting the 90 degree. Understand? So this is the behavior that you are going to see in the vibration. So now discuss the next one, that is the couple unbalance. So now imagine two heavy spot, one at each end of the rotor, but it's positioned 180 degree exactly opposite to each other. So normally you will not find such kind of unbalance where you will find exactly the same weight exactly 180 degree opposite to each other, just to understand what the couple unbalance is. Okay, so what happened that when this spins, the two heavy spot pull on in opposite direction and opposite ends of the shaft, and it will creating a what kind of movement? Rocking movement. Okay, so let's say that one side, the when the drive side movement is of the bearing is going down, or you can say the rotor is going down, and this side it will going up, so it's a kind of a rocking movement. Okay, that's why it's known as this kind of unbalance is known as the couple unbalance. Understand? So now let's in the vibration signature, what you will get here, you will be getting 1x dominant. You will be getting 1x dominant in both radial direction, but the phase readings at the each end of the rotor this time will be 180 degree out of phase. Okay, it will not be in phase. Okay, in the static it was in phase, but here it will be not in phase, it will be 180 degree out of phase because of the rocking moment, right? But if you will be measuring the vibration in the same bearing, the same side, let's say drive end side, horizontal, vertical, so this time also you will be getting the phase difference of 90 degree. Clear? So here in the couple unbalance there will be a rocking moment. Now we will be discussing the third one, that is the dynamic unbalance. So this is the combination, you can say, of the static and couple unbalance. Okay, which is the most common type, you can say, found in the real machines. So the heavy spot are at here at different angle positions and the different axial position across the rotor. So normally if you will look after in the vibration, so here also you will be getting 1x dominant, right? And the phase readings at the two bearing locations are, it can be either in phase or it can be 180 degree, or it can be somewhere in between, we don't know. It depends that whether the rotor is more couple unbalance or more static unbalance. It depends, because the rotor has been weird in at different area. Okay, so we don't know, it depends on that. So somewhere in between you will be seeing, so it's a kind of a most real world unbalance causes that are dynamic. Okay, so normally whenever you will go in the field, so you will be finding almost more than 90% of rotors are dynamic unbalance. Okay, so the fourth one is we will not going to discuss here, but it's also known as the kind of unbalance. It's known as the quasi-static unbalance. It's kind of a special case for the dynamic unbalance, where the static and couple component happen in in the same plane. So we'll not discuss this here because it's not that much important. So now we'll be discussing that, like, exactly that how this unbalance looks like in the data. Okay, data means time waveform, spectrum, in the directions, so how it will look like. So let's first discuss about the time waveform. Okay, in the time waveform, you will be getting a pure unbalanced condition, is very clean and sinusoidal time waveform. Okay, smooth and regular, one complete cycle per revolution. Positive peak and negative peak are equal in height, no flat tops, no spikes, no irregularities. There will be a clean sinusoidal shape in the visual signatures, right? So here what will happen, the rotating force, that means the rotating force is smooth and continuous, producing a smooth and continuous response to the accelerometer, right? So if you just look the same data in the spectrum, what you will see in the spectrum, you will be seeing a dominant 1x peak, or you can say 1x is known as the first multiple of the running speed, and there will be the harmonics like 2x, 3x. There is a possibility of harmonics 2x, 3x, 4x, like this, but either they will be very small or you will not find it at all. Okay, this is how it will be. Okay, so the amplitude of that 1x peak tell you the severity here, and the phase of that 1x, or you can say the first multiple of rpm, will tell us the angular location of the heavy spot. So this is critical. So we cannot balance a machine from amplitude alone. We will be needing the phase, because phase will help us to identify the heavy spot, and amplitude will tell us that the severity, or you can say the how big it is, how big the unbalanced force is. So both are required, but yes, there are the ways where you can perform the balancing by using only the amplitude. I know that, and it can be discussed in the somewhere different topic. Okay, so now come to the third point, that is the direction. So normally unbalance is a radial force, right? It acts outwards from the center of the rotation. So the highest vibration from the unbalance is always come in the radial direction, and radial direction means horizontal, vertical. Actual vibrations for pure unbalance should be very low. In case, let's say the rotor is overhang, so if the rotor is overhang, in that case what you will see, you will be also seeing the axial also more. So radial will be more, but axial can also be more. Okay, so that means if you are, let's say if it's the rotor is not overhang, and then also you are seeing the high axial vibration alongside with the dominant 1x, then you can suspect maybe the misalignment or bend shaft or something different can be there. So that will be needing more analysis or more details. Okay, so now we will be come to the next section where we are going to discuss the what can be the reason for the unbalance. Okay, what can be the reason for the unbalance? We know what is the unbalance, right? That is the uneven deposition or uneven wear of the rotor, right? That will create the unbalanced force. Okay, so what can be the reason for that? It can be the residual unbalance. Let's say the rotor is very very new, and even in the new rotor, some unbalanced force from and there can come from the manufacturing tolerance. That's the reason that why even the new machines are balanced at the factory to a specific grade, and these grades are decided on the ISO 1940, that is specifically for the balancing grades. Okay, and another reason can be material loss, and this material loss can have multiple reasons. Can be corrosion, erosion, cavitation in the pump impellers or wears. Lots of other things can be the reasons can be there, right? And the third one can be will be the opposite of this. The second one is the material loss. Now this one is the metal buildup. Okay, so the problem is opposite. It can be like anything, deposit or scale, or like some process material buildup on any one side of the fan impeller, or that can also create the unbalanced force. And another one can be eccentricity, when the board that is not perfectly concentric with the shaft. So in that case, what will happen, that when the rotor is it's fitted, but the center of mass shifts off the rotation axis. So eccentricity can be the reason, or maybe the rotor distortion, because of the thermal effects, that can be also the reason, right? So normally the overall the thing is this, the important point for our condition monitoring engineers is this, that unbalance is it's not often not the root cause. It's a kind of a symptom. So if a machine keeps going out of balance repeatedly after a balancing, so then we have to look down deeper. Okay, and the balancing is because the balancing is just like treating a symptom. So we have to find out that what's the reason of mass change in the mass distribution. Okay, it's not always unbalanced, there can be other reasons also. So before we wrap up, 3 quick questions, and please pause the video and answer in your head, and please put on your answers in the comment section. So the first question is that let's assume that one unbalanced rotor that is running at 3000 rpm, and I have increased the speed up to 6000. So by roughly how much does the unbalanced force will increase? So there are four options. Please answer your question. Please put on the option correct answer or correct option in the comment section. The second question, let's say that we have measured 1x in the both bearings of the rotor, the phase readings are 180 degree apart, then what type of unbalance can be. Okay, so again there are 4 options. Please put the right answer in the comment section. And the last one is that let's assume that the machine is the unbalance, and which direction we can expect the highest vibration. So 3 options are there. Please answer the correct option in the comment section. So that's the concept of the rotor unbalance, that is fully covered. So in the next video we will be having the practical side, or you can say the practical of this balancing, that how to do the balancing. And actually we will be discussing that we'll be not discussing, but we will be clearly seeing that how balancing is exactly done in the field, or you can say it can be single plane, or so I will be trying to share as much as detail or as much as thing is possible in the practical way, that how you can perform the balancing in the field, so that there should be no problem at all for you all to do the balancing on site. And I will make sure that you will never ever need anyone for doing the balancing in the field after looking after that video. Okay, so please subscribe so that you don't miss it, and drop a comment with your answer to any of the quiz questions. Okay, see you in the next one or next video. Till then, please take care and bye.